hello everyone. It's a very great pleasure to introduce Vasco Carvalho. He did his early education in Portugal and then his PhD at the University of Chicago, where he studied the macroeconomic implications of networks. And he must have, I don't know how he saw where we were all headed, but that's really where we've gone, the discipline has gone. And so he brings with him expertise in three very important fields today: heterogeneous agents in macroeconomics, network theory, and big data. So I don't quite know how he manages to actually be in all these fields. It's very impressive, and so let's hear him. I think that some of the issues that he works on have great importance to countries like India, where you can have macroeconomic shocks that affect people in different ways. And I think the network theory that he works on can really help us see why you can do big things for some people and other people are sort of left out of the system. Vasco tells me that he started off trying to do development economics, and then with Rob Townsend, and then somehow moved into macroeconomics. So this is the year to come back, Vasco, to development economics. Welcome to IIT. It's wonderful to have you here.
Thank you. All right, thank you for the invitation, and given that this is a name lecture, I'm very thankful that the introduction has already been made, but that is an honor to be doing a lecture in the name of one of really grad school heroes, because I was pretty bored with macroeconomics. And those papers were kind of a little bit of a shining light in the mid-2000s, before it became cool. All right, so this is work with Matt Elliott, which is really the brains. I'm just the cheerleader here. And then John Spray, which was a student at Cambridge in development macro search, but he's now a very serious person at the AMES, so I need to tell you that I do not represent the IMF in this talk. All right, so let's move on to pretty pictures. So if you're bored with economics, I don't think we just discovered two water worlds out of Alpha Centauri. That would be exciting. If you're here for the economics, think about two blue goods. Very boring. And there's two plants. And those two plants buy their inputs from a variety of upstream suppliers. They do their own thing, they transform their good, and they supply those goods downstream, which in this particular case, I'll give you a little bit more insight in a little bit, but you're really thinking about wholesalers. And then those wholesalers route it further downstream to kind of final consumption vendors, final demand vendors, right? So kind of this is an example of something that is obviously true, which is production in economies is organized around such chains, in the sense that we have specialized producers. These specialized producers rely on the orderly flow of inputs to produce their own good, do some value added, and then route that good downstream, right? And that's what's happening here from upstream orange all the way to final demand facing firms, right? So what we're going to do in this paper is a question that has been around a little bit, which is, does the structure of the economy, of production in the economy around these supply chains give you any insight into market power? Or in particular, does the location of a particular firm along supply chains confer it market power? All right? And for that's going to come in with a concept, or in the theory we write down, that's going to come up with a concept that we're going to call bottleneck firms. And almost without telling you what bottleneck firms, if you had to vote for bottleneck firms, I think most people would say it's the blue firms, right? And there's a very physical, almost hydraulic sense to it, right? If the flow of goods going from orange to purple needs to be maintained, if I were to remove one of the blue, you would think, what is the economy doing is rerouting the flow of goods around one of the removed blue nodes in order to route that downstream, right? And you would have to have a lot of rerouting if you were to maintain, say, the economy at initial equilibrium with a set of prices and a set of quantities. If you want to maintain the same set of final demand prices and quantities, so kind of attain the same final demand utility for a representative household, you would have to reroute, and that may be difficult under some conditions, which we're going to endow the model with. So that's objective number one, is to think about, if I give you a graph like this, basically with this information and a little bit more, can you immediately pinpoint where market power resides? What are firms that are likely to be having an advantageous position to exploit pricing above marginal cost, given their location in the supply chain? So that's number one. Number two, we want to generalize this. So this is like a very contrived, in a way, it's kind of primed, or it's kind of the easiest I could come up with. All right. In reality, if you want to think about the economy-wide, these supply chains are actually much more complicated. You can complicate this by having one of the green guys supply one of the orange guys. You're introducing a cycle. But you can also have this is one good, which ends up being the purple good. But you could think about many intertwining supply chains, right? In that world, what is this? Is there still this intuitive concept of a bottleneck firm? And how is that linked to market power? That's objective number one. It's a general measure of this. Objective number two is a very applied paper. I want to take this measure. You give me the set of all transactions in the economy, and I give you at scale all the firms that are impeding the economy to operate at efficiency. So I'm going to construct algorithmically, based on my notion of equilibrium, based on my notion, I want to feed possibly to policymakers. You give me the set of all linkages in the economy. I tell you the bunch of firms there are bottlenecks, and according to the theory, that are impeding the economy of working at first best. All right? So I think we've gone through this. So what's going to happen? So we're going to develop a theory. I think general is an overstatement. It's going to be very contrived. So it's really, I don't know what we were thinking when we wrote these slides. It's in a way, it's a proof of concept. All right? And you may have lots of questions of what happens if I relax this, and the answer is I have no idea, because it becomes very intractable. Okay? And the theory will develop this concept of bottleneck firms. So just to I will just repeat this on end. A bottleneck firm is a firm such that given prices, given a current equilibrium, if you were to remove that firm from the supply chain along with all its linkages, the economy could not supply current aggregate demand at current prices. It would supply strictly less. And then it's going to be a one result paper. And I'll give you the result right now. And there's nothing more, really. There's a corollary. If there are bottleneck firms in the economy cannot be at a competitive equilibrium. Prices cannot equal marginal costs, generically, and not only with the bottleneck firms. Okay? Now, the theory is, in a way, what we like about this is that immediately the theory gives you a scalable algorithm that and it's a good place because it's a very pedestrian computer science 101. So there will be basic tools of computer science and machine learning. in kind of, to then enable this serial-led identification of what are these bottleneck firms. And then we're going to roll it out at scale. So what I didn't tell you is that this is not a pretty example. This is a particular supply chain in Uganda, coming from VAT data. So in Uganda, as in many countries in the world right now, we have, say, from VAT tax records, and I understand that some states in India also have this, though not in the whole country, or at least not digitized in the whole country. The complete record of all, in Uganda, of course, of all formal transactions, or VAT tax-paying transactions. Okay? So we're going to just say, the end is just a possibility. We can actually do it. It's feasible to do it. It runs in a week and gives you these bottleneck firms. And then we're just going to do basic correlations of what do these bottleneck firms look like. Okay? So there's two things about this paper. And the first is, well, let me not get into psychology. This is an out-of-date, because I cannot get around to writing the final version. So let me actually step back. So a little bit just as a kind of big picture. I got into this on the macro angle, and as Rohiti was saying, essentially it was always there. There's always been a macro tradition of thinking about macro from the bottom up, or disaggregated view, and where GDP is just a statistical. It has economic value, but it's just an aggregate. And the interesting thing is how it doesn't have a life of its own, right? And that tradition, it goes back to Leontief at least. The first modern general equilibrium model, von Neumann, is a multi-sector model. All the work by Bob Solow and many people on linear systems. The first RBC model is a multi-sector model, right? But it kind of comes and goes. So, but this, what is now called production networks, is a little bit a literature that went back to that and thinking about the propagation of trying to initially do away with aggregate shocks, and just think about, the shocks happening in the microstructure of the economy all the time. Under what conditions do they propagate such that in the aggregate for an outsider it looks like a macro fluctuation, something like a GDP fluctuation, right? So I don't know what an aggregate TFP shock is, but I know what a micro TFP shock is. Windows Vista is a micro TFP shock. It's like, you may not be old enough, but XP was really good. Then they came up with Vista. And if you do like solo accounting at the firm level, you see Microsoft has a huge TFP shock because they put in more resources, but they produce crap. Okay, so it's basically a management or a R&D failure. And once you start that, it becomes a very trivial thing. The definition of a productivity shock makes a lot of sense. Is resources are in place, the technology is in place, but somehow output does not, fluctuated due to some or other reason. So that's very kind of macro feel. But there's always been, and before this production network, there was already lots of work on social networks, and there's people here that are leaders on that. And when I got to Cambridge, I got to interact more with, and they had to bear with me. And for example, Sanjeev was doing papers on trying to elicit notions of market power around, given a little bit like we're going to do today, in a simple way, more general and more beautiful, but also much more, theory can afford to be just the abstract and not go all the way to contacting data. So I kind of just went and bully Matt of, that's fine, we have all these concepts, but what do we actually do with them? Can you do a scalable theory that we can take all the way to data? So there's the production network side. I only listed work that has features of market power. There are others, of course. And of course, there's a lot of different approaches, including, Mihai was discussed yesterday. There is more theory side to this, and Sanjeev has done work there. So there's a lot of different, there's stuff a little bit more computer science and econ, work of Michael Strosky early on, etc. Of course, it's a big deal right now with the rise of market power hypothesis. And in a development context, and we're going to be talking about Uganda, and I'm not a development economist, but there is also some literature there trying to understand, distortions in supply chains as they apply in developing countries, say distortions in the food supply chain, etc. Right? All right. So I'm going to describe an economy, and it's basically going to be a long list of assumptions. Right? And that's the only interesting thing is that for this particular combination of assumptions, I will be able to, even with all these assumptions, I am not going to be able to solve or to characterize much my actual model. But there's a sense, it's not formally a dual, but there's a sense in which there is an almost dual problem to the problem that I'm going to put. From that problem that is highly tractable, I'm going to be able to extract a notion of bottleneck firms, and then I'll have one theorem for you and then one corollary. That's it. Okay? So, the economy works from upstream to downstream. So it's actually not a complex network. There's a clear up and down. All right? Which, by the way, is counterfactual in real-world data. But we'll see in a little bit. It's amazingly not that counterfactual. Right? And I remember bullying Sanjeev. He was putting like directed a cyclical graph, and I was being my loudmouth self, and because I didn't accept this assumption that is allows for a lot of tractability. But now we have data to look at it, and it's actually, reality is not that far from being a pure. So in our world, there's going to be a very upstream, there's going to be raw materials, there's going to be intermediate transformation, so intermediate technology, the goods, and eventually that will flow downstream to the final demand, meaning goods that are only bought by the final consumer. Right? So this is the technology slide. I'll populate with firms in the next slide. But I am going to have, so how do you produce? You combine intermediate goods and some primary factor in the background that I'm not even going to talk about. So some L, for example, some labor. So you produce commodities by means of commodities, period. I'm going to make a strong assumption there for tractability reasons, but also because, so we have it's very difficult, but the few measurements we have, we think that at the very micro level and in the short run, these production functions look very Leontief-y. Right? It's kind of very inflexible in terms of substitution. So I'm just going to impose Leontief production functions for each of the. So when I say, by the way, when I say intermediate goods, there could be arbitrary many. There could be arbitrary many of these layers. All right? And then they're both British co-authors. So when we came with an example, they thought about beer as the example. All right? So it's, it's a fixed proportion technology. We all know what that is. All right? And by the way, you don't need to follow the notation because I kind of removed the most of the math from the slides. I'll try to do this just in words. And again, this upstream, I was mumbling about this upstream downstream assumption. Technically, we're going to impose that technology is directed at cyclical graph. Right? So in essence, I am saying that you cannot, the iPhone goes from rare earth minerals to speakers to integrate in a cellular device. So the assumption is iPhones are not needed to produce rare earth minerals, right? You don't look back. Okay, that's technology. So this is like a depiction of an input-output table, if you want. Call them industries. Now I'm going to populate these industries with firms. And so there's going to be a set of n firms in the economy, arbitrary n. And now, we're going to start adding assumptions. So there's going to be single good producers. There's going to be no heterogeneity, which is against the grain of a lot of heterogeneity on the firm side. So there's going to be, all firms share the same technology in a given industry. Right? So they all produce with the same production recipe, which is, you need say, input D needs 3 units of A and 2 units of B in order to produce, period. So every firm that is in D sector will have to abide by those constraints. Right? Now, and I'm going to assume, constant marginal cost. Right? And to complete the model, I'll also say there's going to be a constant marginal cost of extracting raw materials. And then firms are going to have connections, right? So, and this is where firms, I will endow heterogeneity. So a firm in a given industry might connect to different suppliers, and by those connections, I don't mean that they're necessarily active, that will be determined equilibrium. I just mean the set of feasible suppliers. So if you want to think about, E1, this gets complicated. This is sector E. There is 3 firms producing good E. E1 can only get good C from C1. E3 can only get it from C2. E2 can get it from C1. I'm sorry. E1 can only get it from C1. E3 can get it from C1 or C2. Right? So firms have different suppliers in their consideration set. That's a primitive. And there's perfect substitution across those suppliers. Remember, because they're all producing the same good, there's no differentiation. So, we're going to impose that you just go for the minimum cost supplier, The thing that is probably least standard is we're going to put capacity constraints. All right? This used to be non-kosher. With COVID and supply chain disruptions, people, again, we are going to just impose it. I think there's starting to be some interesting work about trying to really understand or go back to actual classical work of, micro-founding capacity constraints. You could think of information asymmetry problems where the optimal contract is such that imposes limits on what could be traded between 2 firms. You could be thinking more generally about simply geographical infeasibility of trade. So markets are segmented geographically, and I cannot buy ready-mix cement from 300 miles away because it will solidify on the way here. So you can think about it different ways. We're going to endow capacity constraints, and we're going to be general enough for now in which the capacity constraints at the node level, meaning no matter what is current prices in the market, there is a ceiling to the output that the firm can operate. You can think about that as a fixed factor as well, say a fixed factor in a constant returns world. And we're also going to allow for individual links with fixed capacities. So again, there could be physical restrictions on trade. On this highway, you cannot flow more of X units from place A to place B per unit of time. Or you can think about some sort of underlying micro problem that posits limits. And there are, say, information asymmetry problems where that is the optimal contract. We're going to take it as a primitive. All right? So, I don't want to proliferate with numbers, but now there is both the technology numbers, the fixed proportions, and then along each of these edges, there is a maximum capacity and a maximum capacity of production, right? All right. So there's a final demand side that is very boring. I'm not going to bore you with, but no, increasing differentiable man. I'm going to. So what's going to happen in this economy I'm going to endow common knowledge of the network structure. So of all the possible, I know of all my possible suppliers, given my consideration set with the primitive. I know of everyone else's possible suppliers. So I know the entire structure of the economy, which is an unbelievable assumption. And then I'm going to have, given this, all firms simultaneously set prices. So it's going to be a Nash pricing game, actually, on a network. And we're going to demand that markets clear. And once that is done, payoffs are realized for everyone. Right? So an equilibrium in this economy is a long vector of prices, one for each firm. Demand, even longer vector, which is demand schedules, supply schedules, such that the price vector is a Nash equilibrium for firms given feasible supply and demand schedules. And price, demand, and supply clear the market. Okay? And as a definition, as a standard definition, the economy is competitive if and only if all firms produce a price at marginal cost. Okay? Now, I have very little to say about this. Even though I made all these assumptions, it's still very hard to characterize. But here's one that is relatively easy. So it's not really a dual. It has, we can turn it into a planner's version, but it's a funky thing. So let's just call it an auxiliary problem. So take all these firms that I just told you. So by the supplier network, I think we just mean the firms and all their connections. And add a fictitious source node upstream of everybody. If you want to be mystical, call it Mother Earth. And have a downstream sink node where everything flows. So everything flows from the Mother Earth to final demand, if you want to call it like that. Right? So you've had the set of firms, and you're just augmenting that network mathematically by having these two fictitious nodes. All right? And now, and we're going to endow, that will shock some environmental economists, we're going to endow the source node, Mother Earth, with infinite capacity. Infinitely plentiful. Right? Meaning that there's no supply constraints at this very upstream. We don't have a theory, it's a fictitious node. At the final demand, this fictitious final demand node, I'm going to set capacity equal to a demand given prices. Okay? So at this price vector, this is how much can flow in this. If you're a macroeconomist, this is just a final demand aggregator. Okay? Now you can ask the question, how much can it flow from upstream to downstream? From source to sink? That is a relatively bread and butter problem for our engineering colleagues. It's a max flow problem. Okay? So the only thing that is different here if you're a computer science or an engineer is that we additionally have to comply with technology constraints, with this kind of Leontief proportions. Otherwise, you're simply saying, how do I route flow from source to sink, respecting the supply network, respecting that flows have to be non-negative, knowing that you cannot flow more than either the node capacity or the link capacity. All right? And in our case, we've additionally added technology. So it's almost like a planner's problem in the sense that there's no prices, but I've embedded prices there in setting the capacity of the final demand node. But otherwise, it's like the dual, right? It's like now I just have maximize the flow. Now that's, given all the assumptions I made, they finally pay off because this is a linear program. So there's very efficient algorithms to solve this. So again, computer science We'll know Ford-Fulkerson algorithm, CARP algorithm. There's a variety of these algorithms to compute these things very efficiently. In our case, are variations of those that turn more into linear programming because of the additional technology proportions assumption. Okay? All right. So what is this? Think about it, this auxiliary flow problem. You know, forget about everything I told you before. This is simply saying, given the constraints, take a very physical, think of a system of pipes, which is the original network flow problem. You turn on the tap upstream. How much water can you flow all the way to the source per unit of time? That is a function of, that would be unlimited up to capacity constraints in the system, right? Up to, as you keep pumping up the source, they will be, at some point, you know, you cannot pump more because there will not be more throughput in the system. Because the pipes have a certain width, have a certain capacity to carry water. But you can also optimize the routes such that, you know, when that particular pipe in the system is full, I will reroute it another way. Okay? So that's kind of the physical analogy, yeah.
Sorry, Vasco. You have different kinds of water, don't you? They're different goods. So
yes, we will have at some point, so yes, I am in the background, I am rewriting everything in terms of a common numeraire, in terms of real
and what about
unit.
demand? You know, you might maximize the flow only by making widgets or something like that no one wants to consume.
Yeah, they are yes, it is the solution of the problem. In this case, the final demand will be in utils, and so that the problem has no particular, the usual utility properties, all right? But there will be an aggregator, so there is a meaningful a final flow. Okay? So if you've done these engineering problems, you know that the solution of these max flow problems, you know, there are lots of these pipes that they will say make zero marginal contribution to the max flow, meaning they're not bottlenecks, meaning you can if they fail, you can reroute throughput in the system around them at no cost to total throughput. Okay? In a very physical way. So if a pipe in a certain area of Delhi blows up, that does not mean that households will get less water at that moment because they will just be able to reroute around the pipe system. Right? Whenever that is not the case, so whenever water always has to flow through a particular route in the maximum flow, in the solution what is the solution to this is basically the set of paths and the associated maximum flow. And there could be various set of paths. But if a firm attained, so if one of these pipes always has a positive marginal contribution, meaning water always has to flow if you want to maintain that maximum flow, then that is called a positive marginal contribution to the max flow. In our system, right, we have this plus prices and production and transformation. In our system, this simply means that a firm is a bottleneck if and only if supply cannot meet demand at prices, so at a given set of prices, an equilibrium set of prices. If you remove a firm of the network, supply cannot meet demand at the current set of prices. Okay? And that's it. So here's the theorem. An economy is competitive if and only if no firm is a bottleneck. Yeah?
So for clarification, I just wanted to know, between the source and the sink, there are intermediate firms, right?
Yes.
So the objective of ours is to guess who are the bottlenecks and to remove them from the category of bottleneck firms.
Not to remove them, almost fully correct. So our objective is to find out who are the bottleneck firms. Why is that interesting? Only because of this.
Yeah.
Because Even though if you found the bottleneck, then the economy-wise, we cannot be pricing, price equals marginal cost. Removing it is how you find the bottlenecks, is a property of the bottleneck. Like if you remove and flow cannot be maintained, in this case, total output at current prices cannot be maintained. Right?
So these intermediate firms, does they have capacity constraint like the sink one? The source doesn't have any capacity constraint of production.
Yes,
right?
the sink, remember I stressed that.
Yeah.
The sink, you always start from a given equilibrium, which might be competitive or not. There's no restriction there. And that will have a set of prices, and those prices will induce a set of final demand, and in turn, a final demand aggregator. So I'm going to fix that sink to have the same capacity as final demand given prices in that solution. Okay?
So can firms not be active in the competitive equilibrium?
Yes.
So for instance, I mean, in a max flow, on the other hand, you know, the min cut could involve certain flows, certain nodes not having
Same here.
flows. Yeah.
Same here. So they've been made links not operative, meaning they are feasible but no flow is going through them. Say a firm for a given customer is not its lowest cost supplier. Someone needs to warn me when there's like 15 minutes to go, because take E3, in equilibrium, if the capacity here is large enough, E3, the final demand induced by equilibrium prices, the induced demand on E3 might be such that E3 can satisfy everything from C2, and C1, this link will be inactive. By the same reason, if C1 is the lowest cost provider, then this link might be inactive. But if this link is inactive, then C2 is inactive. So there are redundant firms in equilibrium. Yeah?
The prices are not linked specific.
No. The prices are good specific. Yeah?
Just curious as to why not define a concept of marginal bottleneck whereby you don't remove the firm, but you decrease its capacity by X log and determine whether the marginal cost of bottlenecking is going into the price.
Section 6B that hasn't been written. But yes, it's a wonderful idea. You can do that. Okay? But in terms of the theorem, that's enough, right? We can keep with this very blunt thing. I could give you the intuition, but I don't think I have the time. So, oh, wait. I'm sorry. I hate when people do this. Right? Let's just take one of the directions of the theorem. Suppose the economy is competitive, but there is a bottleneck firm in this auxiliary flow problem. So what does that mean? Does that mean that there is a the firm, so the economy is competitive. Sorry, I'm not a theorist. So the economy is competitive. Everyone is so you're starting off, your baseline is price equals marginal cost everywhere. Now you have to think about profitable deviation for a given firm. If there is a bottleneck firm, what the concept of bottleneck in this auxiliary flow is, no matter what you do, flow always has to go through those firms. So that firm knows that it can increase its price marginally, and the flow will not decrease, right? Because that firm is not redundant. Therefore, there cannot be a competitive equilibrium with or price equal marginal cost. That firm has a profitable deviation because it is a bottleneck. Okay, so let me give you an example. B2 is actually a monopolist. It's the only, sorry, that is not true. Okay. Let me, yeah. Let me say how much I want to talk about this, because I've not given you the link capacity, so You just have to believe me that it's possible to construct examples, and you have different types of. So if you think about C1, that is a local monopolist of good C for at least 2 firms of E1 and E2. Okay? So if that firm goes away, we know that the production of good E only can come through E3, because these will not be able to produce. Right? So for Mother Earth to supply the final consumer, you now need to activate. The only way you're going to produce E goods is going to be, because they need B's and C's, is to go through this chain. So if there are capacity constraints on C2, either on the node or on this link, such that, or on E3, or on the links downstream of E3, then C1 will be a bottleneck, in the sense that if I remove it, I cannot reroute the flow around E3 alone. Right? The remainder are examples of this. Here's the last result I have for you. Generically, if there are bottleneck firms, so we've just learned that if there are bottleneck firms, we're not in a competitive equilibrium, price will be above marginal cost, a way not only for bottleneck firms, but for firms that are themselves not bottlenecks. Meaning this is a consequence of distortions, of market power distortions propagating. Okay, so double marginalization, classical double marginalization is happening. So what is this saying is a policymaker, and macroeconomists are already like in a circular shooting squad about markups and how to measure them. Suppose we could measure them, right? I gave you the markups. This would say that a policymaker looking at markups would not be able to cure market power distortions, because a firm that may have positive markups in equilibrium and not be a bottleneck. So to restore competitive equilibrium, all the markups economy-wide will go to 0 if you intervene in the markets containing bottleneck firms. Okay. Now we're obviously loose about, what does that mean? One way or another, you have to increase capacity in the system. Okay? So it means that bottleneck firms have, 2 desirable properties. One is, if they exist, then the economy cannot be at, there's market power. The economy cannot be all pricing at price equals marginal cost. Okay, so I need to now move very quickly. So I want to do 2 things now. So I want to remember the second objective of this paper was to actually go make contact with data. And I won't be able to in 5 or 7 minutes. 15. Oh, that is much better. So I'll go back to the slow self. So there's going to be in theory, so the theorist identification, and then the empirical person that actually deals with real world data. Okay? So theorists, they just assume that all the data exists. So all the supply networks in the economy, all the capacities, you are fine assuming that the economy is in equilibrium as you observe it in data. So then you just go to your engineering and computer science friends and say, look, the equilibrium, the Nash pricing game on a general network, whatever, is horrible. But there's this auxiliary flow problem. And that is very easy to solve. You put those ingredients, and you also need to know technology, by the way, but let's give that as well. And you put it in a computer, and you just solve. So in fact, this is not strictly true because, again, we have these additional linear constraints that the classical Ford-Fulkerson algorithm will not do. But it's a variant of that is close by that has a little bit of more linear programming field. But essentially is you input all this data into Python or MATLAB or whatever you nerdy self decides to elect. And the computer spits out in a fast amount of time. This is the maximum flow attainable. These are the nodes that have a positive marginal contribution. All right. So in particular, I'm already going after myself. What can you do? You put the data, you calculate the maximum flow. And then you iterate. You take one firm out at a time. So the graph is now the original network minus I. Calculate the max flow again. Did the max flow decrease? If the max flow decreased, then that firm is a bottleneck. Supply could not be maintained when that firm, the level of demand could not be maintained given that that firm was removed from the network. Right? So that goes into the list of bottlenecks, and you just do it n times. Because it's a linear program, it's actually feasible. Right? In practice, data is messier, so we're just going to give you a very dirty, again, empirical people will be shocked. So I have lots of problems. Where is this DAG coming from, this directed acyclical graph? What is this mystical source? What are capacities? What is technology? How do you identify? So we're just going to run you through assumptions you could make that probably won't be publishable. So the nerdiest is when you get real-world data, say from this VAT, you get all the firms in the economy and all the links and all the flows and all the values. These are typically not a directed acyclical graph. There are loops. So the iPhone, you do see the rare earth mineral firm buying the iPhone, right? But for any graph, you can think about pruning the graph, so cutting edges, taking edges away from the graph, such that it becomes a DAG, right? I just go to the data and say, forget that the mining firm is buying iPhones. Zero that out. That is actually a basic computer science algorithm, which is the feedback arc set problem, which is, so obviously you don't want to do this, you want to minimize the amount of times to preserve as much as possible the original data, right? So that is the feedback arc set problem, that is, what is the minimum set of edges that you can cut to turn a general network into a directed acyclical graph. That happens to be an NP-complete problem, but there's decent approximation algorithms. So you can go with that. There's actually an example. I learned this from Felix Tintelnot and Magnet Mockstead at Chicago that do this trick in a very different setting. Yes?
Could you move this further? So a bottleneck would only exist within a connected component.
Yep.
So it only makes sense to look within connected components.
Yes.
Could that be a way to figure this out?
Yes, so the VAT data that I'm going to show you is almost immediately, so there's kind of a few weird firms that are not within the giant component, but it's really like a few hundreds out of many thousands.
Secondly, is it, I'm still thinking about it, but is it a necessary condition that, say, the degree centrality of a bottleneck would be higher than an average node?
No, it's not neither necessary nor sufficient. But you have some intuition, but yeah.
Edge capacities and firm capacities, shouldn't they be accounted for when dropping the number of, I mean, you're dropping edges based on just the count, right?
I'm dropping nodes and with it the edges.
Yes.
Again, a more sophisticated is the proposal in the back of the room, right? You do epsilon transformations of capacities.
I suggest we defer other questions.
All right. All right, so once you have a DAG, that procedure immediately gives you a set of upstream firms that have no connection. It gives you a partial ordering in mathematical terms, and you can use that. You'll just get every dangling node that only has downstream links and not upstream links. Add artificial links to this mystical source node, right? Assume, and it's a bigger firm, in the data set we're going to use, we're going to have also the information on final sales. So what is the sales of a firm to intermediates, and what is final to final consumers. So we're just going to use that and set that as the sink and the sink capacity. This is neither here nor there, but we found it cool that we can do hierarchical clustering to estimate Leontief production functions, so I'll just advertise that. And that's like that's where the referees are going to kill us, and we have no patience to deal with this. If you have a panel, set the maximum to the maximum observed flow in your sample. If you don't like that, do 2 times. It's arbitrary, of course, and a lot will depend on that, but you can vary and see. And there's inclusion properties that I'm not going to have time today. So if I do all links have 2 times the capacity, then the remaining set of firms, if any, will be in the original set. So there's kind of inclusion properties that are useful. More generally, I think this points to, if you like this, you really need to think hard about identifying capacity constraints credibly. All right? So, okay, let's do this. So John has, for many years, worked with the Ugandan government on many different things, particularly matching suppliers with customers and at exploiting this kind of VAT database for them through the IGC. This is how the data comes to us. And so we're going to go there. So this is the data we had that we could play, partly, so honestly, right? Arguably, these bottlenecks and market power distortions may be more distorting, more operative in developing country context if you think that there's less of a competitive environment. Again, these are flaky words, right? So what you have is the set of formal firms. Again, development, yes, there will be lots of informal firms. That's why I'm calling. So you now can get away with stuff by calling it a proof of concept, which is you pleading to the referees that don't exact your standards. So that's what we're doing here, okay? So it's like a mega merge. So you have all this VAT data that gives you which firms trade with who, over time, and how much. Then you can merge that with customs data, because we only account for imported goods. So some of those orange goods in the first slide, some of those were internet, like Kalina was talking yesterday. Then we're going to merge that with corporate income tax, where you're going to get a lot of balance sheet variables for these firms as they report their income tax to the government. And a business registry that will tell us stuff like the code of the industry and other covariates. We're going to deflate everything. So it's a relatively small formal economy. Bless you, is 40 times 40, right? It's 40 by 40. That would be a full graph. Everyone is connected to everyone. That is much bigger than 90,000, right? Another way of seeing this is in the data, the typical firm buys from and sells. The typical firm, there's obviously a lot of heterogeneity that is very interesting, but the typical firm buys from a relatively small number of suppliers and sells to a relatively small number of customers in the order of 10. Okay, something like that. In this case, smaller. So that's it. That is a graph visualization package. If there's people that get inspired, there's people that are. But the entire point is you get this messy data, and now we have an algorithm to apply to this to think about market power. Right? So the algorithm is you give me all this data. Step 1, you DAG it. Right? So you're going to start cutting edges and making it to a DAG. As I was saying, so this is my moment of apologies for being the loudmouth in some seminars. It's interesting, no one ever thought about this. It's very DAG. So you have to cut, in particular, value-weighted links. You have to cut only about 4% of all the transactions of these 12 million or of the value of these 12 million transactions to get the economy into a clear upstream, downstream. So there is a sense of the economy is organized. There is a direction that goods flow, right? So there's some sense in this, and Paul Antras, I think Alina talked yesterday about notions of upstreamness and downstreamness, and there's a real sense in which data corroborates that there is a real sense of, that mining is very upstream and whatever. Painting nails is very downstream, right? They're all in there, as long as they pay taxes. So once you do that, we're going to run this hierarchical clustering algorithm to identify Leontief technologies. I didn't say much, but this is important because I have these consideration sets, right? And obviously, I want to have as much as possible flexibility. Remember, I did perfect substitution for the same good. So I'm a firm. I know 5 suppliers of good D. They are, from my perspective, perfect substitutes from the perspective of the model. And this is what it's going to allow all the rerouting possibilities in the network. So when I'm going to calculate network flows, I better know where you can route goods through, given which firms are in which consideration sets. So we didn't want to go, we have a robustness check just on industries. So every firm in the industry, we think about every firm that you ever traded it in an industry, or we can just go into hierarchical clustering and thinking from the history of all trades of these firms, and how can you do this? You can identify firms by they have to move in constant proportions if the technology is Leontief, right? And different goods will have different proportions. So you can try to identify those. So it's a very natural hierarchical clustering problem. I've told you I'm gonna assume away the problem. I'm actually gonna downplay node capacity for this talk. I think we have another version where we tried node capacity. Here I'm just gonna say, oh, node capacity is infinity, so the only constraints here are gonna be now edge capacities for implementation. The results go through, there's nothing hinging on node capacity. And I'm just gonna set it to the maximum observed over the 6 years. So in the back of my mind, there's a sense that there's been enough variability in prices that I could trace out where the maximum of that supply schedule is, right? Where no matter what price happens after that, trades will not increase between those two firms. I'm gonna do the mystical step. I'm gonna add these artificial nodes, and then I'm gonna run. I have no idea what's happening in my Nash pricing game. That's a very complicated game. But I know this, so I'm gonna run this algorithm once, get the max flow in Uganda, and I'm gonna run it 37,000 times more. At each time I remove a firm, calculate the max flow. Is the max flow equal to the original? If yes, that firm is not a bottleneck. Is the max flow smaller than the original? Then that firm is a bottleneck. Okay? And the output is a set of bottleneck firms, which according to my theorem, if that's not empty, the Ugandan economy cannot be pricing equals marginal cost, and I'll now tell you what are those bottleneck firms. So what this does is, once you've so you went from this, so this is the full tax-paying firms in Uganda in a DAG, having cut the edges. And again, this induces an ordering into upstream, downstream immediately. And these are the bottlenecks found by the algorithm. So if you believe, and that's you should never believe anyone, particularly this paper. But if you buy into all the assumptions we made, those are the firms that are responsible for the Ugandan economy not pricing at marginal cost across all producers. There's about 50 every semester. This number varies, but it's always a small number relative to 40,000. So depending on assumptions, I can find 100 firms, I can find 150, but it's a small set of firms. They're very persistent over time, so if I run this semester by semester over this 6-year period, we cannot tell you, because they would come after us, the tax authorities. So I cannot tell you what firms are there. I cannot tell you what those blue firms were in the beginning. It's all around you, but I cannot tell you more than that. But I can tell you sectors that have a higher number. So obviously there is like obvious things that should come up, and they do come up, like natural monopolies. The central bank shows up as a bottleneck. We can remove that, this kind of, is it part of the production network? But it buys and sells. It's integrated in the economy. But so do energy generated, electricity company, whatever. So natural monopolies show up. A lot of agriculture shows up at a lot of different stages, from upstream all the way to final distribution. And many final demand service sector inputs, all right? Non-physical services. And that's what I showed you at the beginning was data. And this is indeed the two, now they're less visible, the two blue firms, which are indeed bottlenecks, okay? There is one particular sector in the economy where there's two plants. One works in one part of the country, the other works in the other part of the country. All producers around the country need to go through those two firms to deliver to the final consumer what they are. So they are local monopolies. Okay, so those are kind of pretty obvious. So I'm just going to finish this with running through, so bottlenecks are larger firms. They have more employees. They're older firms. In accounting profits, this is in logs, so they're much more profitable. In terms of price-cost margins, again, I'm not going to attempt, I've been burned once by computing markups. So let's just go with accounting measures, learner indices. They are double. Someone asked me about centrality. Sanjeev has a beautiful paper that says, under certain conditions, this boils down to between centrality measures. We don't have that result. Our measure is about bottlenecks in max flow problems, and that has no obvious connection to between centrality. But again, there's a very strong sense of flow going through, which is what between centrality. And indeed, between centrality is highly correlated with that firm being a bottleneck or not. If you think about traditional I/O measures, you think about, is the market contestable? What is entry rate? So take sectors. If there is a bottleneck in the sector, I'm going to call it a bottleneck sector. If there are no bottlenecks in the sector, it's a non-bottleneck sector. Bottleneck sectors have lower entry rates and higher concentration, but noisily higher concentration, according to Hirschman. We can use, I told you it's very persistent, but there is variation over time in the bottleneck status. So we can run a panel of semesters. We choose semesters, God knows why. And you can kind of try to think about what happens as bottleneck status changes for a firm. Is that associated with outcomes of the firm? And in a correlational sense with firm years effect, blah, blah. It seems to be, and I'm not going to bore you today, but there's like at some point a war breaks out in South Sudan during the period of our sample, which means a lot of productive capacity that was directed to export across the border, gravity. So there was quite a bit of trade between Uganda and South Sudan. And a lot of the capacity, once the war breaks out in South Sudan, gets rerouted internally. So we try to exploit that as a kind of a natural experiment in which capacity was added to the system internally. Right? This, in the terms of our model, these are links going somewhere else, and that is not in our model. All right, going away from the one final sink. Right? What's happening in reality is that there is the domestic sink and the external sink, and we're just exploiting. A war broke out. Capacity got allocated internally that used to be devoted to exportation. Does that generate arguably exogenous variation in bottleneck status, and does that pad out? And it seems to work. The instrument is okay. It's not particularly strong, but it's there. So I'm going to stop here. We're very excited about extending this. All of this was one firm at a time. Now you can use the same concept and say, okay, forget about one firm. Maybe if I remove that firm is not a bottleneck. But now if I allow me to remove two firms at the same time, are they a joint bottleneck? Where any of them individually is not. You can have such cases. That has implications for, if you take this too seriously, for kind of either tacit collusion or merger possibilities that we're exploiting. All right, that's it. Thank you so much.
So thank you so much. We have time for maybe two questions.
I have one comment and two questions. First, your concept of bottleneck is extremely similar, even though the data are different, that what we call key player in network.
Yes.
So basically the idea, and I did a lot of empirical work, is that we say, okay, if I remove one agent, let's say on crime, in a network, how much total activity will be reduced? And we do 37,000 times, and it is the one that does. That's the first thing. The second thing, which is very important, because it's very complicated what you do, is that you have to show us that if I'm agnostic about your model, and only look at between the centrality, does the 50 firms you identify are the same or not, or is it so I don't have to go all these kind of things, and hopefully it will not be the same. And I saw that you have the slide on that. Or how many are different on the top 50?
So I don't have that number.
If 49 are the same, then it's a bit.
But I can run a. This is not this slide. Here it is. I can run a horse race. This has not been updated to the last.
You could do horse race.
But I can do a horse race. They seem to have distinct information, meaning when you run them against each other, they're both significant. This is purely statistical.
So you look at the ranking in between.
We haven't done that particular ranking.
And the last thing, as you know, the assumption you're making is strong, is that when I remove this firm from your networks and I rerun, I'm assuming that no link can be formed at the same time. So you could assume that you remove this firm and maybe this firm doesn't exist anymore. So in the example of the 2-1, so maybe another firm will take this place, or a link will be formed, and you assume that it's a short-run policy that
So we allow, and we have, so number one, I agree, we can do more, but remember, we allow to have perfect substitution across all suppliers in the consideration set that the algorithm finds as the same good. Then you can say that the algorithm finds, so forget about the algorithm, that is in the same industry and has ever traded with this firm. And you say, this is still very restrictive. So you can say, and allow perfect substitution across all the firms in a narrow SIC sector. And there's a lot of correlation between the bottleneck measures here. So that kind of, now what we don't have is entry, right? And what we don't have is endogenous capacity, which is, if you think this is important, then you have to think about the super game where capacity is defined. And,
One last question back there.
Yeah, I was just curious that in a system with capacity constraints all over the place, one would expect to see the existence of rents all over the place. And the question of market power probably should more be in terms of whether the units are earning their rents as reflected in the Lagrange multipliers of a social welfare maximum, or whether my market power is so strong that I manage to earn everybody else's rent and take it myself. So how much excess rent am I collecting in the system is a more interesting question, for me at least, in the presence of capacity constraints in the system, because there are definitely rent structures.
I don't want to put you on the spot all the time, Sanjeev, but we don't do that. nor do I think we can get there. In the sense that what we, again, this is a macroeconomist kind of being pushy with a brilliant theorist and say, take me all the way to the data. I don't care about our beautiful theorems. Right? So it's maximizing tractability. And one particular question is, if policymakers increasingly have these data sets, and policymakers, I know that the Indian Competition Markets Authority, at least at some point, was mandated to do this, which is, we typically think of those as kind of acting on merger cases, but they have some duty in most countries to monitor, right? But where do they where do they decide to monitor there's no science there. And if you go to the UN, if you go to the OECD, you find these very flaky manuals of, you should look at big sectors, you should look at consumer-facing sectors, you should look at concentrated sectors. But it's very flaky, right? So this is a automated way that should not be taken on its own of kind of, here's a set of candidates of firms that you might want to look at. All right? Quickly. Ingest all the data in the economy. Where are we moving is kind of getting all these transactions in real time just in a data bank. So it's just a way of using that. Because we want to privilege that level of tractability of going all the way to real-time detection tool, we simply we're not very finesse. I do think there are papers in this literature that make the original, the little that I know about the literature of the more micro theory is exactly motivated by that. It's less about production, multiple goods, so all of that is abstracted away. And it's more about intermediation rents. So the fact, can a particular firm or an intermediator in a market be so key? You can think about tolls, right? It's like, if there is only one passage through the mountain, that guy or girl can extract all the rents, including, and that's what you're thinking, from the other tolls along the way, because that makes the value of the transaction feasible. And that's what these guys do beautifully. But then they cannot do this, so I wanted to go this way. Or they've already done it, so I'll only do worse. Yes, and I think that's very important, but that's not what we do.
Thank you so much.
Thank you.